discussing Chapter 1, Methods of Proof for our course BSM 32, Number Theory. Before we proceed, let's define first what number theory is. Okay, number theory is concerned with properties of the set of natural numbers. It is called the queen of mathematics as it helps discover interesting relationships between different sorts of numbers and to prove that these are true. Okay, number theory is partly experimental and partly theoretical. The experimental part leads to questions and suggests ways to answer them, while the theoretical part tries to devise an argument which gives a conclusive answer to the questions. The following are some basic notations and properties of the integers that we will use later. So for the set of natural numbers or positive integers, we use the capital letter N. While for the set of integers, we use a capital letter Z. And we use capital letter Z with the superscript plus to denote set of positive integers, while the superscript minus to denote the set of negative integers. For the set of rational numbers, we use Q. So if it's positive, it's Q plus, and if it's negative, it's Q minus. And then we use the Roman letter R to denote the real numbers. A proof is a sequence of logical statements which gives an explanation of why a given statement is true. Previously established theorems are used to deduce the new ones. One may also refer to axioms as starting points because they are rules accepted by everyone. A mathematical proof is absolute, which means that once a theorem is proven to be true, it is proved forever. Until proven true, the statement is never accepted as a valid one. Okay. There are many techniques that we can use in proving the validity of a given statement. It is important to note that there is no ideal proof. A theorem can be established using different techniques, and none of them is better or worse as long as they are all valid. So in this chapter, we are going to discuss three different methods of proof, and these are the direct proof, the indirect proof, and the proof by mathematical induction. Okay, so let's define first our learning targets. So at the end of this chapter, you are expected to define direct proof, indirect proof, and proof by mathematical induction. Second, illustrate the use of these methods of proof. And then verify some properties of real numbers using these methods of proof, and practice the importance of accuracy and perseverance. Okay, let's determine first your prior knowledge about these topics. So, what mathematical notations are used to represent the following real numbers? Even integers, odd integers, numbers divisible by 5, numbers divisible by 7, sum of positive integers, sum of positive even integers, sum of positive odd integers. Okay, so for even integers, for every n element of z, so that means n is any integer, then 2n is an even integer, 2n plus 2 is the next even, and so on. Hence, even integers can be represented by 2n, 2n plus 2, 2n plus 4, 2n plus 6, and so on and so forth. So, the three dots here represent that this series is continuous. Okay? For odd integers, for every n element of z, then 2n plus 1 is an odd integer, 2n plus 3 is the next odd, and so on and so forth. Hence, odd integers can be represented by 2n plus 1, 2n plus 3, 2n plus 5, and so on and so forth. Okay, for numbers divisible by 5, if even integers are numbers which are divisible by 2, then numbers divisible by 5 are multiples of 5. So for every n element of z, then 5n is number divisible by 5, 5n plus 5 is the next number divisible by 5, and so on. Hence, numbers divisible by 5 can be represented by 5n, 5n plus 5, 5n plus 10, and so on. So the same goes with the numbers divisible by 7. Such such that numbers divisible by 7 can be represented by 7n, 7n plus 7, 7n plus 14, and so on. But for sum of positive integers, for every a and b, which are both elements of the positive integers, the sum of positive integers is represented by a plus b is an element of positive integers. So this is true because the set of positive integers is closed under addition. So meaning to say, they exhibit closure property. The sum of positive even integers, so since we have the notation for positive even integers, let a be equal to 2n and b equal to 2n plus 2, which are both elements of positive integers, then their sum is represented by a plus b is equal to 4n plus 2, element of positive integers. So what happened here was that we added 2n and 2n and then plus 2. So 2n plus 2n is 4n, and then we just add 2. So of course their sum must be an element of the positive integer. Well, for the sum of positive odd integer, the same way goes through it. So for every a equals 2n plus 1, and for every b equals 2n plus 3, which are both elements of positive odd integers, their sum is represented by a plus b is equal to 4n plus 4. Okay, another. Given real numbers a, b, and c, define or illustrate the following properties of equalities: reflexive, symmetric, transitive, replacement, addition property, multiplication property. So I think we have already discussed this in our plane and geometry subject, and I hope that you could still remember those properties. For the reflexive property, a number is always equal to itself. Just like you, when you look at the mirror reflects yourself. So you are equivalent to yourself. So, from the word itself, reflect, reflexive property, it defines that a number is always equal to itself. So, A is equal to A, B is equal to B, and C is equal to C. Symmetric property. We can interchange the sides of an equation and the equation is still a true statement. So, if A is equal to B, then we could also write B equals A. For transitive property, if A equals B and B equals C, then we could deduce that A is equal to C. Transitive property involves three different quantities, assuming that the 2 is equal to the third part. For the replacement, if A equals B, then if we have any equation that involves A and B, in the equation, A can replace B in any instance or vice versa. For addition property, adding the same number to each side of an equation gives us an equivalent equation. So if A equals B, then adding C to A and adding C to B doesn't change the meaning of this equation. So that A plus C is still equal to B plus C. The same goes with the multiplication property. So multiplying the same number to each side of an equation gives us an equivalent equation. So if we multiply C to both sides of the equation, A and B, then we could have A times C is equal to B times C. So that's all for the session. See you next time. Bye-bye!